Welcome to the deep dive. Today, we're ripping the cover off a paper that dives deep into something pretty crucial for the future of AI in science.
Yeah, this one's interesting.
It's titled Defining Foundation Models for Computational Science, a call for clarity and rigor by Choi and a great team of researchers.
And this paper really gets at the heart of a problem we're seeing, well, everywhere right now.
You mean the term foundation model?
Exactly, it's exploded. But applying that label to complex scientific simulation and modeling, it gets messy fast.
Absolutely. So our mission today is to get crystal clear on what foundation models should actually mean in the world of computational science.
Right. And why using the term loosely is, well, causing headaches.
And we'll explore a proposed framework that could actually make these truly foundational tools a reality.
Think of this deep dive as getting a crucial set of coordinates for a landscape that's changing at, like, warp speed.
Yeah, a map, pinpointing where the definition is fuzzy.
And more importantly, where the real potential lies for building powerful, reusable scientific AI.
Okay, let's unpack this. We've all seen the incredible impact of foundation models in other areas, right? Like text or images.
Oh, yeah. GPT, SAM, Stable Diffusion. I mean, they've really changed everything in their domains.
And you can see why people are excited. The paper highlights their success comes from this broad generalization.
Right. They work on tasks they weren't explicitly trained for. It's pretty amazing.
Plus those emerging capabilities that seem to come out of nowhere.
Almost magical, yeah. And of course, they are trained on absolutely massive data sets.
Which is key. So it makes total sense why folks in computational science look at that success.
And want to apply that foundation model label to their own work? Of course they do.
But here's where the paper points to something they call an alarming trend. In computational science, that term foundation model is being slapped on things without a clear, universally agreed upon definition.
And that vagueness is causing real problems. It's not just, academic nitpicking either. Well, this lack of rigor, it dilutes the term, right? If everything's a foundation model, then nothing really is.
Okay.
It makes comparing different models incredibly difficult, like trying to judge apples against oranges, but they're all just labeled foundation fruit.
Yeah, I get that.
And in science, where reproducibility and validity are just paramount, this ambiguity really undermines rigor. We need to know exactly what these models can and can't do.
It's interesting to contrast that with the workhorse methods computational science has relied on for decades.
Oh yeah, things like the finite element method, FEM, or finite volume method, FEM.
These aren't data-driven in the modern AI sense, so they aren't foundation models, according to that ML definition.
No, they're not. But they are incredibly foundational in another sense. They are domain-agnostic FEM, works whether you're simulating heat transfer or structural mechanics.
Right, broadly applicable.
Across countless problems and geometries. And crucially, they are mathematically grounded, with decades of theory behind them.
So they set a very high bar.
A very high bar for what a truly foundational tool in science should be. Versatile, reliable, and you don't need to reinvent the wheel every time you tackle a slightly new problem.
So if I'm hearing you right, the paper is saying we don't just need data-driven models for computational science, we need a clear definition of what a foundational one looks like.
Exactly. Something that bridges the power of AI with the rigor and versatility of those traditional methods.
Okay. And that brings us to their proposed solution, right? They don't just point out the problem.
No, they put forward a formal definition, specifically tailored for computational science.
Okay, let's hear it.
They define it as a data-driven model trained on a broad distribution of scientific application types or physical systems, which exhibits wide generalization capability across scientific problems, computational domains, tasks, and physical conditions.
Okay, there's more.
Without requiring retraining from scratch or structural modification, and serves as a reusable base.
Wow, okay. That's a mouthful, but every part seems really carefully chosen.
It is. Let's break down those key pieces because they really tell you what to look for.
Go for it.
Data-driven model is the first part, obvious maybe, but important. It learns from actual scientific data, simulations, experiments.
Capturing complexity traditional models might miss.
Right. Different from just hand-coding physics rules. Then trained on a broad distribution.
That sounds crucial, to avoid models that only work on one niche problem.
Precisely. It needs exposure to diverse physics or scenarios during training, so it learns general representations of the underlying physical world rather than just memorizing specific solutions.
Okay. And then the big one, exhibits wide generalization capability. This feels like where the foundation part really kicks in.
Absolutely. It has to work well on problems it hasn't explicitly seen before. New geometries, different boundary conditions, maybe even related physics.
Because if you have to start over for every slightly different problem.
It's not foundational, it's just another specific model.
Got it. And the kicker, without requiring retraining from scratch or structural modification.
Yes. Adaptation should be minimal, like fine-tuning, not a complete rebuild.
Which makes it scalable, reusable.
Exactly. Otherwise, the computational cost would just be prohibitive for widespread use. It wouldn't really be a reusable base.
Okay, that definition is pretty tight, but the paper also lists some other characteristics that are highly desirable for these scientific foundation models. What else should we be looking for?
Well, scientific consistency is huge. That's a big one.
Meaning?
Should ideally respect known physical laws. Conservation of energy, symmetry, things like that.
Right. If a model predicts energy appearing out of nowhere?
It's basically a non-starter for most serious scientific applications. Trust is paramount.
Makes sense. And robust extrapolation.
Yeah, predicting reliably outside the exact conditions seen during training. Science often pushes into new regimes, right? So a model that just collapses when you tweak a parameter slightly isn't very useful for discovery.
Okay. Data scalability seems straightforward. More data, better performance.
Pretty much. It shouldn't hit a wall too early. Performance should keep improving with more diverse, high-quality data.
And finally, something often missing in pure ML mathematical rigor.
Yes. This is key for trust in science. Can we analyze its stability? Can we understand error bounds?
Get some theoretical guarantees.
Exactly. For high-stakes scientific predictions, we need more than just it worked on the test set. We need some level of theoretical backing.
So for you, the listener, maybe wading through all the AI hype out there,
Yeah.
this definition and these characteristics, they give you a solid checklist, don't they?
They really do.
Does this model claiming to be foundational actually meet these criteria? Helps cut through the noise.
It really does. But okay, if we have this clear definition, why aren't we just swimming in computational science foundation models already?
Good question. What makes building these things so much harder than, say, building GPT?
Well, the paper lays out several fundamental challenges, and they are fundamental.
What struck me most was the sheer scale of scientific data.
Oh,
We're not talking about text tokens or, small image patches here.
not even close.
A single scientific data point, like a 3D simulation snapshot, fluid flow, structural stress, it can have millions or even trillions of values.
Trillions. It's hard to even wrap your head around it. Gigabytes, maybe terabytes, for one simulation result.
So what does that mean for training?
It fundamentally limits your batch sizes, puts immense pressure on memory, and it makes it incredibly hard to capture complex physics across diverse conditions because you simply can't process data from a truly massive number of these high-fidelity simulations during training.
Standard AI architectures just weren't built for that kind of input scale.
Not at all. And then there's the fine-tuning challenge.
Right, they're supposed to be adaptable.
But in computational science, the downstream tasks are wildly different. You might pre-train on fluid dynamics.
But then need to adapt it to solid mechanics. Or a totally different geometry.
Or a new type of boundary condition, or a higher resolution. The variations are extreme.
So adapting isn't easy.
Often, you need to significantly modify the model or retrain large parts of it. Techniques like LoRa or prompt tuning, which work wonders in NLP, they're much harder to apply efficiently here.
Which undermines that whole cost-saving, reusable base idea.
Exactly. Then there's data heterogeneity, another huge hurdle.
Meaning the data comes in all shapes and sizes.
All shapes and sizes. Scientific data isn't just text or pixels. It's scalars, vectors, tensors defined on complex meshes or point clouds.
Across different spatial and temporal dimensions.
Representing totally different physics, building a single architecture that can ingest and understand all of that. Incredibly complex.
And we don't have the big standardized data sets like in other AI fields.
Severely lacking. There's no equivalent of ImageNet or Common Crawl that spans multiple physics domains. Where's the standard data set for, say, coupled thermal fluid structural problems?
Which hampers pre-training and benchmarking.
Massively. Plus, simulations are often tied to a specific mesh or grid representing the geometry.
Mesh dependence.
Yeah. A model trained on one mesh might struggle to generalize or even work on a different one. That's a real portability problem.
Okay, what else? Physics constraints.
Yes, integrating those fundamental physical laws, conservation, symmetry, boundary conditions, directly into the neural network architecture without sacrificing generality. That's a major open research problem.
It's a tricky balancing act. You need it to learn from data, but also obey the known laws of physics.
Precisely. And trust and interpretability, non-negotiable in science.
You need to understand why the model gives a certain prediction, especially for high-stakes stuff like designing aircraft or predicting climate change.
A black box just isn't sufficient.
And multi-scale and long-time behavior.
Capturing phenomena across vast spatial and temporal scales in one model. Think nanometers to kilometers, microseconds to centuries. Many scientific problems involve this multi-scale behavior. Building a single AI model to handle that effectively, extremely difficult.
Wow. Okay, so it's definitely not just about throwing more data or bigger models at the problem.
No, these are fundamental architectural challenges, data challenges, physics integration challenges, unique to computational science.
It makes that alarming trend of mislabeling maybe more understandable, because building the real thing is hard.
It absolutely is. But the paper is optimistic, which is good.
Okay.
It suggests that building these models is attainable. And the key might be looking back to those successful traditional methods we talked about, like FEM.
Okay, tell me about that. How do they propose bridging that gap between the traditional and the AI?
They introduce a framework. They call it the Data-Driven Finite Element Method, or DD-FEM.
DD-FEM, okay.
And it's explicitly inspired by the sort of elegance and rigor of classical FEM.
So it keeps the idea of breaking a big problem into smaller pieces, the elements.
Exactly. It keeps FEM's compositional structure. You decompose the global domain into these small subdomains or elements. But here's the twist. It replaces the traditional fixed polynomial basis functions within each element.
With data-driven bases?
Yes. Bases learned from data.
Okay, walk me through the concept. Like that figure 2 in the paper illustrated it.
Right. So step 1, you generate training data.
Right.
But crucially, you do it from diverse, small, computationally cheap subdomains.
Not the massive, expensive, full problem simulation, just little pieces.
Exactly. Local data generation, cheap and easy. Step 2, you train these data-driven basis functions on those small data sets.
So the basis functions learn to represent the complex behavior within those small pieces from data.
Precisely. Step 3, you assemble the global domain using these trained data-driven elements, just like you would assemble elements in classical FEM. You're building the big picture from these smart trained pieces.
Okay, makes sense so far.
Right. And step 4, this is critical for the scientific consistency part.
Yeah.
You solve the underlying governing equations, think Navier-Stokes, elasticity equations, whatever, on that assembled global domain using these data-driven elements.
Ah, so that step ensures that the global solution still respects the fundamental physics laws.
Exactly. It enforces them explicitly at the global level. You're getting the best of both worlds.
Data-driven power locally, physics rigor globally. That sounds elegant.
It is quite elegant. And the practical advantages are significant.
Like what?
Well, those data-driven bases can be far more expressive than simple polynomials. They can capture much more complex local physics.
And I assume because they're more expressive, maybe you need fewer of them. Or you can use larger elements.
Potentially, yes.
Yeah.
Which means you could perhaps solve much larger, more complex global problems much more efficiently than with traditional FEM and its typical element sizes.
Okay, but the biggest advantage, the one tackling one of those core challenges we discussed,
Right.
it seems to be how it handles the data scale issue.
Yes, this is where it gets really powerful. DD-FEM essentially decouples the training data scale from the global problem scale.
Say that again? Decouples the scale?
Yeah. You train your data-driven bases on small, cheap simulations of local behavior, little snippets of physics. But then you can use those pre-trained bases to assemble and solve absolutely massive, complex global problems.
Problems you couldn't possibly run full simulations for to get training data directly.
Exactly. This directly addresses that massive data point size challenge we talked about. It's a huge bottleneck removed.
Wow. So you could potentially build up a library of these data-driven elements, train on different local physics,
Right.
and then sort of mix and match them, assemble them to solve novel, large-scale problems without needing global training data.
That's the vision.
Yeah.
And that aligns perfectly with their foundation model definition, doesn't it?
Let's see. It's data-driven,
Check.
trained on a distribution of data, albeit localized,
Yeah.
and reusable for arbitrary large systems without retraining the basis from scratch for the whole problem.
Check. It fits.
Yeah.
And because it still solves the governing equations globally.
It naturally promotes scientific consistency, more trust.
More trust, more verifiability. It also has clear potential for data scalability. Training the local bases on more diverse, high-quality local data should just make the overall model better.
What about fine-tuning? Does this help with that challenge?
It should significantly reduce the cost, yeah. If you need to adapt the model to a new global problem, maybe change the geometry slightly, or the physics in one region, you might only need to update or retrain a small subset of the local basis functions relevant to that change.
Not retrain the entire global model from scratch.
Exactly. Much more efficient.
This could also help with the lack of standardized data sets, couldn't it?
How so?
Well, because the training data is local and therefore cheaper to generate, it becomes much easier to actually create, curate, and share data sets for specific types of local physics or subdomains.
That's a great point. The paper mentions something called the WELL dataset as a potential example resource for this kind of local data sharing.
And importantly, it might inherit the mathematical rigor of classical FEM.
That's a key goal. Because it builds on that FEM structure, you can potentially derive stability conditions, convergence proofs, error estimates for the combined data-driven and classical framework.
Yeah.
Much harder to do for pure black box neural networks.
So the paper really positions DD-FEM as this bridge, trying to bring the best of those, battle-tested numerical methods together with the power of modern AI.
That's a perfect way to put it. It's a framework that lets you leverage data-driven expressiveness, but keeps it grounded within a mathematically sound compositional structure.
So how do you actually create these data-driven bases?
Right.
What are the nuts and bolts? What techniques does the paper talk about?
Okay, so a primary approach they focus on is using compression-based methods.
Compression, like zipping files.
Yeah, not quite. The idea comes from component-reduced order models, or ROMs. You take that high-fidelity simulation data from the small subdomains, the local data, and you compress it. Find a lower dimensional representation that captures the essential behavior.
Using what? Things like SVD, principal component analysis?
SVD is one way,
Yeah.
That gives you linear basis functions. It's efficient. But you can also use nonlinear techniques like autoencoders or even JANs.
Neural networks for compression?
Exactly. These are more expressive. They can capture more complex local behavior like sharp gradients or turbulence. But they are computationally more expensive to train, of course.
Okay, so you compress the local data into these bases. Then what?
Then you project the governing equations onto that compressed representation onto those bases. This gives you a much smaller system of equations to solve within each element.
Which is computationally cheaper.
Much cheaper. And this compression approach is powerful because it often allows for mathematical rigor, things like error analysis based on the compression level.
Okay. And the paper mentioned different ways to actually stick these compressed pieces, these elements, together globally.
Right, the assembly process. They discuss methods like static condensation, which enforces continuity strictly, or residual minimization, or discontinuous Galerkin methods, which allow for some jumps between elements, but enforce consistency in a weaker sense.
Each with trade-offs, I guess.
Yeah, trade-offs in computational costs and how strongly continuity is enforced. The key is that the assembly process combines the local learned behavior with the global physics equations. And using those neural network compression methods is especially exciting for creating really expressive, learnable local bases.
They also briefly mentioned other potential ways to create the data-driven bases, right? It's not just compression.
No, exactly. It's presented as a flexible framework. You could potentially use things like symbolic regression or sparse regression.
Trying to find actual equations for the bases.
Yeah, discover interpretable mathematical functions directly from the local data, like a data-driven version of traditional enriched FEM methods like XFEM or GM's-FEM.
Interesting. Or implicit neural representations, like NERFs. Or neural operators.
Exactly. Using networks that map coordinates directly to solution values within an element. That can potentially make the method mesh-free and resolution-independent locally.
Lots of possibilities. And you can mix and match.
Yes, hybrid basis construction. Combine different types of bases within the same simulation. Maybe use traditional polynomials where the physics is simple, and these powerful data-driven bases where it's complex or poorly understood.
Okay, this all sounds great conceptually, but does it work? The paper provides actual numerical results, right? To show this DD-FEM approach isn't just theory.
They do, and this is where it gets really compelling. They show several demonstrations, mainly using those compression-based methods.
Like the extrapolation in space example. That sounds important for tackling the data scale problem.
Yes, this is key. They train models using data from small subdomains only,
Right.
and then show they can accurately solve problems on much larger, completely unseen global geometries. They did this for a complex lattice structure, a porous media flow problem, even a transient Burgers flow problem.
And the results were good.
Very good. And the speedups were massive. We're talking over 1,000x faster for the lattice, around 24x for porous media, over 600x for the Burgers flow compared to running the full high-fidelity simulation.
With low error.
Yeah, relative errors consistently below 1% to around 4%. That's not just a minor improvement. That's potentially a fundamental shift in computational efficiency enabled by learning that local behavior.
Okay, that's impressive. They also showed generalization in source functions.
For a simple Poisson equation, they trained the model using easy sinusoidal source terms.
Whoa, okay.
But then tested it by asking it to predict the solution for a complex, completely unseen spiral wave source.
And
it worked. The error was only about 0.7%. It shows the learned bases captured something more fundamental about the PDE response, not just the specific training sources.
And maybe most fascinatingly, generalization across PDE types. This really points towards that broad applicability goal.
This result was particularly exciting, I thought. They trained a single neural network decoder, part of the compression model, using data generated from both the Poisson equation, which is elliptic, and the Burgers equation, which is advection-dominated. Very different physics.
Okay. So one decoder learned from two different types of equations.
Yes. And then that single trained decoder could accurately predict solutions for both types of equations under unseen parameter conditions.
Wow.
It even extrapolated the Burgers solution spatially to a larger domain it hadn't seen, with low error. Around 6% error for the Poisson part, maybe 1 or 1.5% for Burgers.
That suggests you might not need completely different data-driven bases for every single PDE type out there. There might be some shared underlying structure it can learn.
Exactly. It hints at the potential for a single data-driven framework to support diverse physics.
These results really make the case that DD-FEM isn't just a neat idea, it's a potentially powerful working framework.
It reinforces their point that DD-FEM is presented as a flexible philosophy or framework for building scientific foundation models. It allows for different implementations, but sticks to those core principles: modularity, using local data, and enforcing global physics.
Now, the paper doesn't stop there. It also takes a critical look at other models out there that have been called foundation models in computational science. They evaluate them using their own proposed definition.
Right. They look at examples based on things like Fourier neural operators, FNOs, DEPA nets for accelerating solvers, graph neural networks for materials or chemistry, transformer models for molecules, vision transformers applied to fluid dynamics, a whole range of recent work.
And they're careful to say they aren't trying to diminish these works, right?
No, not at all. They acknowledge these are often significant advances in their own right.
They're just asking, do these models measure up to the specific, rigorous definition of a computational science foundation model that we just discussed?
Exactly. And based on their criteria, it's summarized really well in Table 2 of the paper. They point out common areas where many of these impressive models currently fall short of being truly foundational in the sense they define.
Such as? What are the common shortcomings?
Well, a frequent one is the lack of explicit physics-based constraints.
We talked about that. Not building in conservation laws. Symmetry.
Right. Many empirically effective models don't explicitly build in or enforce these fundamental laws, which means they can sometimes produce predictions that are physically unrealistic.
And that limits their ability to generalize or extrapolate reliably, especially to new situations far from the training data.
Exactly. Another common point is the domain-specific nature of the generalization.
Meaning they generalize, but only within a narrow field.
Yeah. A model might be incredibly general within the space of, say, linear elliptic PDEs, or within a specific type of molecular simulation, or maybe only for a steady fluid flow.
But it doesn't generalize across different physics domains, or across different modalities, like from image analysis to fluid dynamics simulation.
Generally not, or at least not in the broad way envisioned by the paper's definition for a computational science foundation model.
And some might lack that mathematical rigor we discussed earlier, the theoretical framework for error analysis, stability guarantees.
Precisely. That's often harder to establish for purely data-driven deep learning models compared to methods built on established numerical analysis principles.
So the takeaway from this comparison isn't that other models are bad,
Not at all.
but that many currently labeled as foundation models in science don't fully meet these specific criteria, particularly around scientific consistency and really broad cross-domain generalization.
Correct. Which leads them back to advocating for these hybrid approaches, like their DD-FEM framework.
Approaches that deliberately try to integrate data-driven learning with established physics-based frameworks.
Yes, to try and bridge that gap between just empirical effectiveness and genuine scientific trustworthiness and broad applicability.
Okay. So wrapping this all up then, what's the big takeaway message from this paper?
I think the main message really is that clarity matters. If we're going to use a powerful term like foundation model in computational science, we need rigor. We need a clear definition.
And the paper provides one, plus a potential framework, DD-FEM, that shows a path forward.
Exactly. A path that seems to combine the strengths of classical methods, their structure, their rigor, with the power of modern AI.
And that DD-FEM framework, with its focus on localized data and modularity, seems to cleverly address some of those really tough challenges we discussed earlier, like the data scale problem.
Absolutely. It makes large-scale data generation and reuse seem much more feasible.
Plus its extensibility. You mentioned it could draw on both traditional FEM ideas, like adaptive mesh refinement, and AI concepts like transfer learning or pre-training.
Right. It seems like a really promising and flexible direction for future research.
But the paper isn't claiming to have the final definitive answer, is it?
Yeah.
It ends with some really interesting open questions.
No, definitely not the final answer. And those open questions are great. They really highlight how much is still left to figure out in this space. Like, are there other frameworks besides DD-FEM that could meet this proposed definition? Is this even the right definition, or are there other, maybe better ways to think about foundation models specifically for science?
That's a fascinating one. And how essential is strict physical consistency? You know, if a model is incredibly accurate empirically, does it truly matter if it violates a conservation law by a tiny amount in some edge cases? Where's the line?
That's a tough one. And a really practical question. How do we actually benchmark these things? How do we certify them? How do we track progress towards truly general-purpose scientific models? What would a standard evaluation even look like?
What kinds of data sets do we need to build to test this versatility?
And the question about scope really stuck with me, too. Can a model that's only focused on, say, fluid mechanics still qualify as a foundation model if it's incredibly general and reusable within that single domain?
Or does foundation inherently imply generalization across different scientific domains?
Yeah. What's the boundary? These questions really show this field is still in its early days. It's going to require a lot of ongoing discussion, collaboration between different scientific fields and the AI community.
It feels like the paper is making a strong plea. Let's not just chase the hype around the foundation model term.
Right.
Let's actually define what we're trying to build and make sure it meets the incredibly high standards that science demands.
Exactly. Building these powerful AI tools for science is incredibly exciting, no doubt. But we need to do it thoughtfully, rigorously. Are we just building slightly better surrogates for existing simulations? Or are we building truly foundational, trustworthy pillars for the future of scientific discovery and engineering?
So we've taken a deep dive into this compelling paper by Choi and the team. We've explored the urgent need for clarity around foundation models in computational science.
We've looked at the significant challenges, data scale, heterogeneity, physics consistency.
And we've examined the promise of frameworks like DD-FEM, which try to leverage the best of both classical numerical methods and modern data-driven approaches.
We've seen that defining these terms rigorously isn't just playing with words. It's essential for guiding research effectively, ensuring reproducibility, and ultimately building trust in these powerful new tools.
And DD-FEM provides a concrete example, a potential path towards models that are not only powerful and general, but also scientifically consistent and maybe even mathematically rigorous.
Ultimately, the paper serves as a powerful call to action, really, a call for collective reflection within the community. As we develop these incredibly capable AI tools for science, how do we ensure they truly live up to the name foundation?
How do we make sure they provide a reliable, trustworthy base for the next generation of scientific and engineering breakthroughs? That's a question for everyone involved in this work to consider.
Absolutely.
Thank you for joining us on this deep dive.